In this episode, we are going to build a clear mental map for several networking ideas that often get introduced separately, even though they make much more sense together. New learners hear about the Open Systems Interconnection (OSI) model, the Transmission Control Protocol (TCP), the Internet Protocol (IP), Internet Protocol version 4 (IPv4), Internet Protocol version 6 (IPv6), and the Virtual Private Network (VPN), and it can feel like a stack of unrelated technical terms. The real breakthrough happens when you stop treating them as isolated vocabulary and start seeing them as parts of one larger story about how data moves from one place to another. Networking is easier to understand when you ask where a concept belongs, what job it performs, and how it connects to the concepts above and below it. Once that map becomes clear, many security topics also become easier, because firewalls, segmentation, remote access, and secure communications all depend on understanding how these layers and protocols work together. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at CyberAuthor.Me in the Bare Metal Study Guide series. A useful starting point is the idea of layered communication. When one device sends data to another, many different things must happen at once, but they do not all happen in the same way or for the same reason. One part of the process deals with the physical path, such as radio signals, cables, or hardware connections. Another part deals with local delivery on a nearby network. Another part handles logical addressing across larger networks. And another part manages whether information arrives reliably and in the right order. On top of that, software still needs to format data in ways that users and applications can actually understand. If you try to picture all of that as one giant, shapeless activity, it would become almost impossible to reason about clearly. Layered models solve that problem by dividing the work into smaller responsibilities, which helps people design, troubleshoot, secure, and explain networks without getting lost in every detail at once. The OSI model is one of the most useful teaching maps for that layered view. It breaks communication into 7 layers, starting from the physical movement of signals at the bottom and rising toward application interaction at the top. The model is not a literal step-by-step script that every real network follows exactly, and that is an important point for beginners. Its value comes from helping you ask the right kind of question about a problem or a control. If you are dealing with a cable issue, a wireless signal issue, or a switchport problem, you are thinking near the lower layers. If you are dealing with addressing, routing, or path selection, you are thinking in the middle. If you are dealing with application behavior, data formatting, or how software sessions behave, you are thinking higher up. The OSI model gives you a structured way to place concepts in context, which is why it remains valuable even though real-world networks are often described more practically through the TCP/IP suite. At the bottom of the OSI model are the physical and data link concerns, which are closely tied to how devices actually connect and communicate on a local network. The physical layer deals with the raw movement of bits as electrical, optical, or radio signals. This is where cables, connectors, wireless transmissions, and hardware interfaces belong conceptually. The next step up is the data link layer, which helps devices communicate with nearby neighbors on the same local segment and organizes data into units that make sense for that local delivery. This layer is concerned with whether data can move from one device to the next immediate point on its path, not whether it can cross the entire internet from city to city. For security learners, that difference matters because some controls focus on local traffic behavior, hardware connections, and nearby network segments, while others focus on broader routing and policy decisions farther up the stack. Knowing where local delivery ends and broader network delivery begins is one of the first major mapping skills to develop. The network layer of the OSI model is where IP becomes central. This is the layer concerned with logical addressing and the movement of packets across different networks rather than just within one local area. A device on one network may have no direct local relationship with a device somewhere else. So the network layer provides a way to identify endpoints logically and move traffic through routers until it reaches the correct destination network. That is why IP addresses matter so much. They are not about the physical cable or the wireless signal itself. They are about identifying where data should go in a larger interconnected environment. This is also why routing belongs here, because routers examine network layer information to decide the next hop toward a destination. When beginners hear that the internet is basically a network of networks, this layer is a big reason why that statement makes sense. The network layer is what allows local networks to be linked into something vastly larger and more flexible than any single isolated segment. The transport layer sits above the network layer and deals with how data is delivered between endpoints in a more organized way. This is where TCP is especially important. TCP helps manage reliable delivery, ordered data handling, and the general idea that a conversation between two systems should be tracked carefully enough that missing or out-of-order pieces can be noticed and handled. That makes TCP valuable for tasks where correctness and completeness matter more than raw speed, such as loading a web page, sending a file, or logging into an application. Not all transport traffic works this way, and that is why it also helps to know about the User Datagram Protocol, UDP, which is simpler and does not emphasize the same kind of reliability tracking. The key beginner lesson is that IP gets data toward the destination network and endpoint, while TCP helps manage how that data is delivered as a structured exchange. One handles broader addressing and path movement, while the other helps shape the quality and reliability of the conversation. The upper layers of the OSI model can feel less concrete at first, but they are still very useful for understanding what applications are actually doing. These layers are often described as session, presentation, and application concerns. The session idea relates to managing the ongoing communication relationship between systems. The presentation idea relates to how data is formatted, transformed, or represented so both sides can interpret it correctly. The application idea relates to the services that software actually uses to communicate, such as web traffic, email behavior, or file transfer logic. In everyday real-world networking, these top layers are not always treated as sharply separate, which is one reason beginners can feel confused when comparing the OSI model to practical network behavior. The value of these layers is not that you must memorize artificial boundaries between every software function. The value is that they remind you that successful communication is about more than just moving bits and packets. Data must also make sense to the software and users at the far end. This is a good point to connect the OSI model to the TCP/IP model, because the two maps are related but not identical. The OSI model is usually taught with 7 layers because it gives detailed conceptual separation, while the TCP/IP model is often presented more practically with 4 broad layers: link, internet, transport, and application. The link layer roughly covers what OSI describes in its lower local communication concerns. The internet layer corresponds closely to the network layer where IP lives. The transport layer includes TCP and similar transport behavior. The application layer in the TCP/IP view groups together much of what OSI spreads across its upper layers. Beginners sometimes think one model is correct and the other is wrong, but that is the wrong comparison. The better way to think about them is that OSI is a teaching framework with finer conceptual detail, while TCP/IP is a more practical model tied closely to how real internet communication is commonly described and implemented. IPv4 is the older and still extremely common version of IP. It uses 32-bit addresses, which are commonly written in dotted decimal form and are much easier for humans to read than long binary strings. Because the address space is limited, the world eventually ran into the problem that there are not enough unique public IPv4 addresses for every device to have one directly on the global internet. That limitation shaped many real-world networking practices, including the heavy use of private addressing inside local networks and the use of network address translation, NAT, at boundaries where traffic moves outward. For a beginner, the most important idea is that IPv4 solved the original need for large-scale logical addressing very successfully, but the internet kept growing far beyond what early designers expected. Even so, IPv4 remains everywhere, which means modern learners must understand it well. Much of today's internet still depends on it, and many organizations continue to build, secure, and troubleshoot environments where IPv4 remains the main operational reality. IPv6 was developed to address the scale and long-term limitations of IPv4. Its address space is vastly larger, using 128-bit addresses, which makes it possible to support an enormous number of unique addresses without relying on scarcity-driven workarounds in the same way. Its written form looks very different because it uses hexadecimal notation separated by colons rather than the dotted decimal style many people first learn with IPv4. At first glance, this makes IPv6 look intimidating, but the core idea is still familiar. It is still about logical addressing and moving packets across networks. The difference is that it was built with a much larger future in mind and includes design choices intended to improve efficiency, flexibility, and scalability for modern networking. Beginners should not think of IPv6 as an optional side topic that only matters to specialists. It is part of the present and future of networking, and understanding its purpose helps explain how the internet is evolving beyond the limits of earlier design assumptions. A very important mapping skill is understanding that IPv4 and IPv6 do not represent totally different kinds of networking. They are two versions of the same fundamental network layer idea. Both provide logical addressing and support routing across networks. Both help devices identify destinations and move packets toward them through interconnected paths. The differences are mainly in address size, notation, some supporting behaviors, and the broader design choices that came with later development. Many real environments use both at the same time, which means learners should not imagine a dramatic day when the world completely switched from one to the other all at once. Instead, networks often operate in mixed conditions where systems, applications, and providers support one, the other, or both. That coexistence matters for security because policies, firewall rules, logging practices, and troubleshooting habits must account for both versions when they are present. A network team that understands only IPv4 thinking can easily miss visibility or control gaps once IPv6 becomes active in the environment. The VPN concept fits into this map as a way of creating protected communication across an untrusted path. A VPN does not replace all the underlying networking ideas you have learned. It uses them. The basic goal is to create a logical tunnel so data can move across a public or otherwise untrusted network in a way that provides privacy, integrity, and controlled access between the endpoints. This is why people often use VPN technology for remote users connecting back to organizational resources or for site-to-site communication between separate networks. The important beginner lesson is that a VPN is not magic invisibility, and it is not the same thing as the internet itself. It is a protected path built on top of existing network communication. Depending on the design, a VPN may operate with controls and protections that involve multiple layers of the overall model. That is why understanding layering helps so much. You can see the VPN not as a mystery box, but as a secure construction built using addressing, routing, transport behavior, and encryption-related protections. A practical example can bring the full map together. Imagine a remote employee using a laptop from home to reach an internal business application through a VPN. The laptop first uses a physical or wireless connection to join the local network and reach the internet. Local communication handles immediate delivery to the nearby router or access point, while IP addressing helps guide the traffic outward across multiple networks. The VPN software on the laptop creates a protected tunnel to the organization, allowing traffic to travel across the public internet while remaining shielded from easy exposure in transit. Inside that path, TCP may help manage a reliable session for the application traffic, while the application itself presents data in a format the user understands on the screen. If the organization supports both IPv4 and IPv6, those network layer decisions may vary depending on the environment and destination. The important point is that the communication still makes sense as a layered process. The VPN adds protected transport across an untrusted path, but it does not erase the rest of the networking map. Another reason this topic matters for security learners is that many defensive tools and policies make more sense once you know where they fit in the map. Firewalls often inspect network and transport information to make decisions about what traffic should be allowed or denied. Segmentation relies heavily on addressing, routing, and boundary control. Remote access security depends on understanding how VPN paths connect outside users to inside resources. Monitoring and troubleshooting often require you to notice whether a problem seems physical, local, routing-related, transport-related, or application-related. Without a mental map, security can feel like memorizing device names and rule types without really knowing why they exist. With a map, you begin to see that different controls are enforcing boundaries at different parts of the communication process. That is a major step forward for a beginner, because it turns networking from a list of abstract terms into a logical environment where each concept has a place, a purpose, and a relationship to the others. By the end of this discussion, the most important thing to keep is not a pile of disconnected definitions, but a clear picture of how they fit together. The OSI model gives you a detailed teaching map for layered communication. The TCP/IP model gives you a practical way to understand how real internet communication is commonly described. IP operates at the network layer to provide logical addressing and routing across networks, while TCP operates at the transport layer to support reliable data exchange. IPv4 and IPv6 are two versions of that same network layer idea, with different address scales and design characteristics. A VPN builds a protected path across an untrusted network by using underlying networking concepts rather than replacing them. When these ideas are mapped clearly in your mind, networking becomes much less intimidating and much more useful, especially as you move into security topics that depend on understanding how data really travels, where controls can be applied, and how trust is extended or restricted across the path.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.